Welcome back to the deep dive. If you work in the digital world, chances are you are running on Linux, whether you know it or not.
Oh, absolutely. It's everywhere. From massive cloud servers to, the tiniest embedded devices.
And for something so ubiquitous, its foundational security architecture, the system that dictates who can do what is often treated like a total black box.
And that's a huge mistake.
Mm.
Linux security isn't just one firewall or, one admin password. It's a highly configurable, deeply layered system.
Right.
If you're only relying on the basic file permissions you learned on day one, you're missing the entire story of how modern systems protect themselves.
Okay, so let's unpack this. Our mission today is to move past the basics, the simple idea of I'm the administrator, and dive into the precise hierarchical structure of permissions. We're looking at everything from a user's unique digital ID through traditional group access and all the way up to the surgical power of specialized capabilities.
And the sources we looked at are clear. It's a delicate structure of files and commands that must align perfectly.
It absolutely requires precision.
It does. Because the moment you misalign that structure, you risk everything. At best, you get a file access denied error. At worst,
An unbootable system.
or a massive security hole.
Exactly. We're aiming for knowledge that provides not just technical competence, but true security insight.
Let's start at the very bedrock then. Identity. How does Linux even begin to know who you are? It sort of ignores your actual username, right? It really just relies on numbers.
Correct. The system identifies every user through their unique numerical identity, the user ID or UID. And the central source of all this identity information is a surprisingly simple, plain text file, etc. password.
A user directory of the whole system.
Pretty much.
I always found it fascinating that something so fundamental to security is, at the end of the day, just a text file. If you open that up, you see the entire user story laid out in a colon-delimited format.
It is. It's like a compact, single-line database record for each user.
And that format is so critical. Oh, it is. You have the username, then a placeholder for the password, the unique userid, which is the UID, the primary group ID or GID. Then you have user info, the home folder path, and finally the user's default shell.
Every single field matters, and the positioning of those colons is gospel.
Yes, and this inherent simplicity, the fact that it is a text file, is exactly what makes it so fragile if you handle it incorrectly.
And the sources gave a really strong safety warning about this.
They did. While technically you can manually edit, etc. password because it is just plain text, that is very strongly discouraged.
For stability reasons, I assume?
For massive stability reasons.
Yeah.
The format is so unforgiving that if you slip up one character or misplace a colon, you can corrupt the user database and query.
And you're locked out. Or worse.
You can render the system completely unbootable.
So the practical safety tip is to always use the dedicated tools, like a deucer.
Exactly. That command handles all the low-level file edits for you, ensuring that delicate structure stays intact and follows all the protocols.
Okay, so the UID identifies the individual. But security and access often need to scale beyond just one person.
And that's where we move from the individual to the collective, which means we have to talk about groups.
The power of a group is efficiency, right? It lets us apply permissions to dozens, maybe hundreds of users all at once.
Precisely. Instead of configuring each one individually, a user has to belong to at least one primary group, which is the one listed in etc. as pass one.
But they can, and usually do, belong to a lot of other groups at the same time.
Correct. And all that detailed membership info, which users belong to which other groups, is stored in a separate, equally critical text file, etc. group.
Which I'm guessing mirrors the same structure we just talked about.
Yes, it's very similar. It uses a colon-delimited format defining the group name, a password field, which is often unused, the unique group ID, and then the group list. Just a list of the member usernames.
And to manage all this, there are specific commands. You have group add or add group to create a new group.
And then user mod, if you need to modify an existing user, to add them to that new group.
So we've established who you are and what teams you're on. Now the big question is, what can those teams actually do?
And that brings us directly to the traditional gatekeeper, the user group other model. UGO.
UGO, combined with read, write, execute access types.
This is the fundamental three-part permission system of Linux.
So UGRWX. The system dictates access for the file owner, the permissions for the group that owns the file, and then, the permissions for everyone else. The other category.
And the system checks them in that specific order. What's crucial to understand, especially for an audience who might already know the basics, is that R, W, and X mean very different things depending on if you're looking at a file or a directory.
Right. For a regular file, it's pretty straightforward. Read is viewing contents, write is altering them, and execute is running it as a program.
Simple enough.
But directories are where that execute permission suddenly becomes this like fundamental security feature, not just about running code.
It's the key distinction. For a directory, read R lets you list the contents, so running Ls, write W, lets you create or delete files inside that directory.
But execute
X is the permission to traverse or enter the directory. If you don't have X permission, you cannot CD into it, even if you know the exact names of the files inside.
That sounds like a classic beginner pitfall. You might have read access to a file deep inside some folder, but if just one of the parent directories on the way down doesn't grant you execute permission,
You're completely locked out.
Yeah.
The system can't even get to the file's address. It respects that structural gatekeeper first.
and when you run the command cell, this whole security manifesto is laid out for you.
It is, yeah. A lot of information crammed into one line.
You get the file type indicator, a dash for a file, D for a directory, and then that long permission block, 3 sets of AldoX.
For owner, group, and others. And right after that, you get the space-separated details.
Yeah.
The owner name, the group owner, file size, modification date, and all that.
If you can read the output of L as L, you can quickly audit the security posture of basically anything on the system.
Absolutely.
But the UGO model is robust, but it's rigid. It only gives you 3 categories.
Right.
So what happens if I have a complex situation? I need a user, Sarah, to have read-only access to a file owned by the finance group, but Sarah is only in the marketing group.
Yeah.
And I don't want to open it up to other parents.
And that is exactly when the UGO model fails to meet real-world needs. And that's when we bring in the modern exception layer. File access control lists, ACLs.
ACLs are the fine-grained control system. They coexist with the UGO model, but they let you punch holes or set specific rules for individual users or arbitrary groups.
It's really important to understand the prioritization here. ACLs act as specific exceptions.
Okay.
So when the system checks permissions, it looks for an ACL rule first.
Yeah.
If a rule exists that explicitly grants or denies Sarah access, it uses that rule, period.
And if there isn't one?
If, and only if, no specific ACL rule applies, then it defaults back to checking the traditional user, group, and other permissions.
So it's basically an override table for the general rules. And what tools do we use for this?
We use the dedicated utilities setvehicle to, well, set the ACLs and get vehicle to view them.
And a quick note, our sources mention that depending on your distribution, you might need to install these tools. They aren't always there by default.
That's a good point, especially on a minimal install.
Okay, so we focused on what files you can touch. Let's shift now to what commands you can run. This takes us to the mechanism for controlled elevation, sudo.
Sudo. It's short for super user do, and it is the modern controlled gateway to elevated access. It lets a normal user temporarily run one specific command as the super user.
The philosophy behind sudo is the principle of least privilege, isn't it? Only giving the power you need for the time you need it.
Exactly. It severely limits the blast radius. If you are logged in as a full root user and you accidentally type armman up tiro user,
Your system is gone instantly.
gone. But if you use sudo, you only use that root power for the specific command you authorized, which dramatically reduces the chance of a catastrophic error.
And this is why newer secure systems like, say, Ubuntu 20.04 and later, or Kali, they actively discourage or even block direct root login by default.
Right. Why have the root account active if we have sudo? Running an entire graphical session or lengthy tasks as a full root shell is it's too dangerous for daily operation. It's a key security best practice now.
But you can't just run sudo out of the box. You have to be authorized first.
Correct. That authorization is granted by being listed in a very specific protected location. A user must be a member of the privileged sudoers group.
And that's all managed in the it's a sudoers file.
Yes, and you add users to that group using the reliable usermod command, just like adding them to any other group. The fact that the list of who can use sudo is itself so protected just shows how critical it is.
Limiting that blast radius is the perfect transition to what I think is the most insightful concept in Linux security and what provides the real deep dive value here, post-accepts capabilities.
This is where things get really advanced and frankly fascinating. For decades, root privilege was this enormous, indivisible, all-or-nothing thing.
A process either had all the keys to the castle or none of them.
Exactly. Capabilities fundamentally changed that entire paradigm.
So capabilities solve the I need one specific key, but the system only gives me the whole keychain problem.
That's a great way to put it. They take that monolithic root power and divide it into dozens of smaller, highly specialized privilege units.
It's like atomic power.
It is. These capabilities are assigned to processes to let them precisely bypass or enable specific privileged actions without needing the full superuser context.
Mhm.
It enforces the principle of least privilege not just on the user, but on the program itself.
Give us a few examples from our sources to really illustrate how granular this gets.
Certainly. Let's say a process needs to make arbitrary changes to file ownership, the UIDs and GIDs. It needs the capgIWN capability, and that's it.
It doesn't need access to the network or the ability to load kernel modules.
Not at all. Or for something really dangerous, like ignoring all the UGO and ACL checks we just discussed.
There's a capability for that.
There is. It's called CAPTIC override, Data Access Control Override. That is serious power, but again, it's isolated. An application only gets this single key, not the whole ring.
The case studies here really drive the point home. Let's talk about the ping program.
Ping is a classic example. It needs to use raw sockets to send its echo requests, which traditionally required root.
But you don't want to run ping as root.
No. So instead, the system simply assigns it the capnetraw capability. The program can run as a normal user, and the OS grants it just enough privilege to touch the network layer in that one specific way.
And the same logic applies to complex tools like Wireshark.
Right. The main graphical interface, the GUI, doesn't need any elevated privilege at all. But the underlying packet capture tool, dumpcap, does.
So instead of running the entire potentially vulnerable GUI as root, which is a massive security risk,
Only the dumpcap binary is assigned the precise capabilities it needs for network sniffing. It's a surgical approach to privilege management. High functionality without sacrificing security.
Okay, so we've covered identity, access rules, and command execution power, but none of this works if the user identity isn't verified in the first place.
Which brings us back to authentication methods and, crucially, password storage.
Right.
Authentication is just verifying identity. We break it down into three fundamentals. Something like a password,
Something you have, like a key or a token.
and something you are, like biometrics. For traditional Linux login, the primary method is still the password.
We started by talking about the etc password file, and we mentioned that the password field usually just contains an X. That X points to where the real secrets live.
That X is a placeholder. It's a security measure indicating that the system's password database is in the highly protected etc shadow file.
And that file is protected because the passwords inside are not plain text.
No, they are hashed and salted.
Why the intense protection? Why hashing and salting and not just, say, encrypting the password?
Because encryption is reversible. Hashing is a one-way street. The OS never stores your actual password. It only stores the result of the hash. When you log in, you type your password, the system hashes that input, and then it just compares the two hashes.
If they match, you're in.
Right. But the crucial layer here, the really important part, is the salt.
Because in the early days, attackers could pre-compute hashes for common passwords in what were called rainbow tables. Salt defeats that.
It does. Salt is vital. It's a unique, random piece of data that is appended to your password before the hashing starts. This means that even if 1,000 users pick the password Spring 2024,
the unique salt for each user ensures that all 1,000 of those passwords produce a completely different, unique hash in the etc shadow file.
Exactly. So an attacker can't just pre-compute one hash for Spring 2024 and use it to break into 1,000 accounts. They're forced to calculate the hash for Spring 2024 combined with your specific salt, a unique computation for every single user.
It just makes brute force attacks computationally infeasible.
It's the modern defense against bolt password cracking. Absolutely.
And finally, we should quickly touch on the simplest security measure, which is just denying access entirely.
Right. Sometimes you just want to lock an account, and the sources show a simple way to do that. If you place an invalid or non-hashable value in the password field of etc shadow, you effectively lock that account. No password can ever generate a matching hash.
And this is often how the root account itself is disabled on systems that prefer sudo.
It is.
So what does this all mean for you, the listener? We've covered the entire security hierarchy of a modern Linux system, from the numerical foundation of UIDs and GIDs, through the rigid UGO rules, the flexible ACL exceptions, the controlled elevation of sudo.
And finally, the surgical power distribution via POCX capabilities.
It means that Linux security is not a single door you unlock. It's a sophisticated series of interlocking mechanisms.
And this layered approach, what we call defense in depth, is precisely why Linux remains such a robust and reliable platform for, well, everything critical in the world.
Absolutely. And to leave you with a final thought to consider that builds on all this, If capabilities divide the massive power of the root user into dozens of smaller individual pieces, what are the implications for application developers who only need one tiny sliver of that power?
Like the ability to bind to a low port number or read raw network data. How does the complexity of managing all those different capability flags still result in a system that is far more secure than the old all-or-nothing approach?
It's a worthwhile
It
exercise.
really is. Take a moment to explore the complete list of capabilities referenced in our sources. Dig into the Man Capabilities page and see just how surgically defined that power distribution truly is. That is your next deep dive.